Hi, welcome to lecture 4.2. So today we're going to be talking about Riemann sums. So the key idea of integral calculus is that there's going to be a connection between the rate of change of a quantity, so some number, and the total change of the quantity. So we're already used to this idea in sort of simple situations. For example, suppose we have a car that's driving at constant speed, 10 miles an hour. Every single mile, every single hour, he goes another 10 miles, right? So I ask you, how far has it gone after 3 hours? Think about that for a second. Probably 30 miles, right? How did I get that? Well, maybe I just knew it, but I can also think about this multiplication. 10 miles an hour, maybe times 3 hours. We know it's going to be 30 miles altogether. And, you can think, like I said, every single hour, he goes another 10 miles. So after hour 1, it's 10 miles. After hour 2, it's 20 miles. After hour 3, it's 30 miles. We're used to thinking in those terms. So I mentioned rate of change versus total change before. So our rate of change here, right, it's a speed, miles per hour kind of number. And my total change is this total 30 miles, right? So we know that if every single hour I go 10 miles, that's related to the total change. Basically by doing this sort of process, right? Sort of adding up the little bits of change over the individual hours in a way that accumulates to get this total change by the end of the 3 hours. So what we're going to see is that, this situation is a simple situation where I have a constant speed. And so it makes sense just to add up 10 miles, 10 miles, 10 miles. But we're going to have varying speeds, and we're going to have more complicated things, like different situations, but that we can still sort of think of as rates of change and totals of quantities. So let's think about this first example in terms of a graph for reasons that will make sense very soon. So let's graph the car's velocity function. So I know it's a constant velocity, but when I say constant speed, constant velocity, that means that at every single moment I have the same speed, right? It could be that my speed is different at different moments. Right? Maybe in the first hour it's 10 miles an hour, second hour it's 20 miles an hour, something else. That's more complicated. But there's some function, right, that tells me at every point in time what speed do I have. We were talking about velocity and position functions last time. But just remember, like the whole point of this is an input and output, right? The input is time. What time is it? And then, equals the output. Sorry, I shouldn't really have an arrow there. Equals the output, which is, if for velocity, my speed. So I could have different speeds at different times. And if I do like v of 0, that means my speed at the beginning. If I do like v of 10, that's my speed at time 10, and that might mean something different depending on the story. If here we're doing like in hours, then maybe this is speed after 10 hours, but it could be something else. So we can write down velocity functions, right? For example, maybe my velocity function is like t, right? V of t equals t. That's a function that we know about. This would mean that, at time 10, my velocity would be 10. But at time 100, my velocity would be 100. So my velocity is increasing over time. I could have different velocity function. I could have maybe t squared. So at time 10, I square this number, right? 10 squared, whatever that is. So at time 10, my speed's 100 now. And maybe at time, 5, my speed is 25. So it can depend on the speed can depend on your time in lots of different ways. These are two examples of two functions. A really good function we'll be using sometimes is a constant function. So in this story, this car up here is driving at 10 miles an hour. So I'm going to write v of t equals 10. Right, it's a constant function, right? That means that it's always 10, no matter what time it is. At the beginning, v of 0, they're going 10 miles an hour. But also at, time 100. They're also still going 10 miles an hour. So the output is always 10, no matter what the time is. So when I say constant function, that's the kind of thing I'm talking about. It's okay to write something like this, right? Even there's no t's over here, that's fine. And if I'm going to graph this, I'll probably be thinking of like y equals 10. Even, my variable's name is v here, that's the velocity. But if I'm more familiar with graphing stuff that's like y equals, I can think about y equals 10. So let's graph this, right? Time, velocity. I could draw some units. Time 1, time 2, time 3. At the beginning, at time 0, their speed is 10. At hour 1, their speed is also 10. At hour 2, their speed is also 10. At hour 3, their speed is also 10. So I'm getting a nice flat function. And it's going to keep going, right? But in this story, we're only looking at the first 3 hours. So we have a nice horizontal line. So cool, that's a graph of a function. We will see in a minute a nice connection, maybe you can spot it before I talk about it, between this exact calculation that we did up here. We did 10 times 3 is 30. There's going to be a connection between that calculation and something visual, geometric about the graph. So I'll let you think about that in the background. How would the graph change if after 1 hour the car accelerated up to 20 miles an hour? So let's think about how this graph would change, right? At the beginning, it's still 10, right? So up until the first hour, it's 10. So I can have this constant speed of 10 all the way up to the first hour. But then suddenly, at hour 1, the car accelerates to 20 miles an hour. So now, from time 1 onward, it's suddenly 20 miles an hour and maybe staying 20 miles an hour. And we still have hour 2, hour 3. Okay, so now let's think about what the total distance would be. So for the first hour, right, they're still going 10 miles an hour the whole time. So maybe 10 miles an hour times 1 hour. So that's 10 miles total. But then for the next stretch of time, right, they're going 20 miles an hour for how long? For 2 hours, right? So they're going to go 20 miles an hour times 2, 40. So there's 2 legs of the trip, right? On the first leg of the trip, they're going 10 miles an hour. That's only an hour. And then the second leg, they're going 20 miles an hour. But that's for 2 hours. So they cover 10 miles, then they cover 40. Altogether, they're covering, well, we have to add them up, right? So we're covering 50 miles. Okay. So let's just bump this up a little bit more, right? So at the beginning, we did this normal just multiplication to think about speeds. And we thought about it as this graph here. We had a new situation where the speed could change partway through. The speed could have lots of different things going on. Let's do one more. Suppose the car's velocity looks like this. So it's going to be 2 miles an hour for 1 hour. So let's just start drawing. So for the first hour, it's 2 miles an hour. Then it's 4 miles an hour for the next 2 hours. So up until time 3, it's going all the way to 4 miles an hour. And then for 3 more hours, so all the way up to 6 here, now it's going 6 miles an hour the whole time. So I suddenly jump up to here and do that. So I kind of the stair step thing, right? And as I go over time, my velocity is represented by what the height is. We can still do the total distance, right? For the first hour, it's 2 miles an hour. So 2 times 1, so that's 2. Then I have 2 hours here from 1 to 3, and they're going 4 the whole time. So 4 times 2 is 8. And then I'm going 6 miles an hour for 3 more hours. So that's 18. And my total distance, I can add this all up, right? This is 28, I think. So the point we're seeing here, right, is that this regular multiplication makes sense for a constant speed. But even if the speed is not constant, we can still do that multiplication just on different pieces, right? For the first, I can do the first hour and the second hour separately and just add up the distances. Let's think about this geometrically just for a second. The multiplication we did up here at the beginning, 10 times 3, I want to think about that as on this graph, I have a width of 3 of under the graph, and then I have a height of 10. So I have this rectangle right here. Right, this rectangle is 3 wide and 10 tall, which means that like the area of this rectangle is 30. Right, area is length times width. So the length is 3 and the height is 10, so 30 area altogether. It turns out this is a little bit weird at first, but thinking about this number as like the area under the graph of the function is going to be the right way, useful way to start thinking about it. Let's look at that in the next one. Right, where's my rectangles? Well, I have one rectangle here, and I'm actually going to have another rectangle sort of here. So I have 2 rectangles. The first one is 1 by 10, so I have area 10. The second one is 2 by 20, so I'm going to have area 40. Altogether, right, this area is going to be 50 area, just coming from adding them up. So I have a velocity function, and the area under that velocity function, if I want to visualize it as these rectangles, is giving me my total distance changed by doing that velocity. Let's just look at this one, the bottom one. Where's my rectangles? Well, I have one rectangle for the first hour, and have another rectangle from 1 to 3, and another from 3 to 6. So I'm not making any choices here, right? It's just when the speed changes, I make a new rectangle. First one's 1 times 2, second one's 2 times 4, which is 8. And then the last one is 6 times 3, which is 18. So 28 total area. So far, so straightforward, right? I can do my total distance. But it's just worth thinking about this just for a second. Like, I didn't tell you how far I went when I drove the car, right? I just told you how fast I was going. So what this is kind of showing us is that, like, if I know how fast, if I know my velocity profile at every moment, I know I'm going this speed at this time, and this speed at this time, and this speed at this time, that's actually enough information to figure out the total distance that you went, right? If someone says they drove for 60 miles an hour for 3 hours, they had to arrive somewhere that's at most like 180 miles from wherever they started, right? So I get this information on the total change that's possible based just on the velocity information, which is a little weird, right? Because velocity, like we saw last time, I maybe want to think of velocity as like the derivative of position. So I'm kind of recovering information about the total change even without having the original function, which is kind of interesting. So we're going to see that more and more as we go. I'll just say this right now. So I'm going to talk a lot about this stuff called Riemann sums, and we're going to do all this math. But I just want to say right now what sort of the upshot is, what the plan is. Right here, we had a constant function, and then a function that changed a little bit, and then a function that changed a little bit more. Right, what's the plan? Plan is I want to have a continuous velocity function. I want to have something like, okay, my velocity starts out somewhere, and then I smoothly get faster. I smoothly accelerate. And then now my velocity is, constant again, and then maybe I go slower and slower and slower, and I go all the way down to 0 velocity. And now I have negative velocity, which means I'm going backwards. And then I'm flat again, and then I go up, I want to have any function in the world that I like as a velocity, and I want to be able to think about the total distance that I traveled. This area under the curve is going to be the right idea. If I have a function like this, if I have a way of coming up with this area, so it's the area, I'm saying area under the curve is what I've been saying. It's really the area sort of between the curve and the x-axis. So for this first chunk, I have this area. For the second chunk, I have this area. So it's between like the arc of the function itself and the x-axis. And then for the third chunk, I have this area. This part under here is sort of going to be counted as negative because you're going backwards. Like I said, your velocity is negative. Maybe I'm going negative 10 miles an hour. That means I'm sort of building up backwards motion instead of forwards motion. So that's going to like count against our total. But the total area, you know, this part, maybe take away this part, add this part, like that total area is going to be measuring the distance you've actually traveled if you know this velocity function. So that's going to be pretty powerful. I'm going to be able to take any velocity function and figure out the total distance. And the real plan is not just velocity functions. Velocity is a very like good physics intuition to have, but it's going to be any situation where you have a quantity that's changing. You can figure out the total change by looking at the area under the curve. Another spoiler before we continue is how are we going to think about getting the area under these curvy curves? So basically, we're going to do this. But when we do this, it's going to be an approximation for the curvy curve, right? So if I get a red pen. So, right, what could I do? I could say, well, maybe I do my rectangles idea from before, but maybe I just sort of, you know, eyeball what the height's going to be. Maybe I have these rectangles that I've like picked just sort of randomly how wide they're going to be. And I pick a height to the rectangle that, you know, sort of is close to the height of the function. You know, I could keep going. Maybe I think that this like red area is like a pretty good approximation for the area under the actual curvy curve. That's basically what we're going to be doing. We're going to be doing approximations using a finite number of rectangles. And, you know, you could actually do that totally without any calculus. That's a pretty natural idea. Like, how do I count up this total change? I just count up a little bit of change, you know, over small little chunks. That's usually how like things that measure velocity and stuff work, right? They just sample, you know, every second. I check how fast I'm going, and then I write that all down, and I get something which maybe would look like this. The sort of magic of calculus, which is what's going to happen, is that I'm going to be able to have my function. I'm going to be able to pick not just those rectangles, but move on to skinnier rectangles. So skinnier than I started with. Plan after that is to make even skinnier rectangles, and so on. So I make skinnier and skinnier and skinnier. My picture is horrible, but I make skinnier and skinnier in rectangles, and you can imagine that sort of in the end, maybe if I have like the skinniest possible rectangles, it really is like filling in smoothly like all the inside stuff. You might remember from Calc 1, we have this thing called a limit, which is something about doing something maybe an infinite number of times or an infinite way. So we're going to take a limit, more and more rectangles, to turn our approximations into the true areas under the curves. And it turns out there's going to be a really nice way to do that sort of algebraically, which is kind of the point of what we want to learn in this class. So that's sort of where we're headed. But the basic example you want to have in mind always is cars moving, and maybe its speed is changing, and we got these rectangles. And we can add up the areas of each rectangle to get the total. Okay, so let's keep going. So this total change that I've been talking about, so a fancy word for it is Riemann sum. So Riemann was a mathematician. They named it after him for some reason. So we're thinking of the total change of the function over the interval, and it's the area under that graph. So like it says here, we're going to see pretty soon that there's actually a really interesting connection between Riemann sums and antiderivatives. So last lecture we talked about antiderivatives, and this is not obvious at all, but there's going to be a connection between this area under the curve idea and the antiderivatives that we did last time. And the fact that there is that connection is sort of why anybody cares, why this class exists. So we will get to that very soon. Okay. So for setting up a Riemann sum, right? This adding up thing that we did, that's a Riemann sum basically, but there's going to be some sort of fancy notation that we're going to use to make the process easier to write down when we have a large number of rectangles. Right here I have just 3 rectangles, so it was easy enough for me to do this, but we want to write down if there's like 100 rectangles without having to actually write everything, is the plan. Especially because we're going to do taking a limit, so we're going to want to write down sort of abstractly for an abstract number of rectangles as well. Okay, so there's a couple ingredients for setting up a Riemann sum. Given any function, continuous function, we can try to compute the Riemann sum. The ingredients we need are the function itself, f of x. It could be a table, so with an example down here it's going to be a table, but it could also be a formula, like f of x equals x squared or something. We're going to need a starting value, I'm going to call it a, and an ending value, going to call it b. So like here in this car example, we started at time 0 and ended at time 6. So we're always going to need that data. I need to know how far I'm going to go. We're going to need a choice of subintervals between a and b. So that's just a fancy word for like how to chop up the x-axis. So in this car example, my subintervals are like, I could write them like 0 to 1, right? That's one interval, and then like 1 to 3, and then 3 to 6. So we have these intervals, which are breaking up the range from 0 to 6. Typically, they're all going to be the same width. So in my car examples, I made them not the same width just to show you that you can do that. It turns out it's going to be easiest to have them always be the same width, and it'll work. You can still do it, but to have like a uniform sort of system for doing this, it's going to be easiest to have uniform width. We're going to have a certain number of subintervals. So here we chose 3 subintervals. We might use the letter n sometimes to stand for a specific but unknown number of intervals. So like if I say make a Riemann sum with n intervals, that means I haven't told you how many, but it turns out we're still going to be able to write down something for that. And then the last thing, I haven't really talked about this yet, a choice of left, middle, or right. What does that mean? Well, if we think about looking at our curve, our function, so I have to decide exactly how to place the rectangles on here. When I was drawing before, I just was kind of eyeballing it, but we're going to want to have a very specific way of doing it. Specifically, like, say my first rectangle, say the width is going to be to here, and I'm going to start drawing my rectangle going up. I need to decide how tall is my rectangle going to be. I need it to like have something to do with the height of the function, right? Like I don't want to end it down here, and I don't want it to go like all the way up here, right? It has to be like close to the function, but I want to be specific and consistent. So one choice you could make is say, okay, on this interval, let's just, say this is 1 here. Let's just see where 1 goes on the function, maybe right there, what that y value is. All right, this is f of 1. Just keep that in mind. Right, if this is my function, f of x, the y value at 1, I could write as f of 1. So I could just have that be the height of my rectangle. So I would maybe draw this horizontal line, draw all the way down to there. That's that's a rectangle. Let's see if I can do that a little better. Okay. So I could do that, and I would want to continue to consistently make that choice as I go. So now, when my input is 2, maybe I go up to f of 2 and have that be the height of my rectangle. So that I know that's the tallest point. I move over because I know it's going to touch there, and I move down. So you could totally do this. So this is choosing the right endpoint of your interval to be the height for the function, for the height of your rectangle. So that's choosing right. But I could have made a different choice, right? Say I had the same function, but say I wanted to pin the height instead. So I still have 1 here and maybe 0 here. Let's just have f of 0 be the width of my rectangle. And then for my next rectangle, I'll go up here to f of 1. This is f of 1, f of 0, and I'll have the height pinned to that. And this is 2, and I go up to f of 2. So you see how this is different than the other one? Over here, the height of the rectangles was determined by the f, so the function's value, at the right endpoint of the interval. And over here, the height of the rectangles was determined by the function's value at the left end of the interval. All right, I'm thinking of these intervals like the 0, 1, 2. Over here, I still have 0, 1, 2. But for these rectangles, I used I used f of 1 as the height, and I used f of 2. Whereas over here, I used f of 0 and f of 1. So I'm kind of using these right-hand points versus using these left-hand points. So it's a little bit pedantic, and it's not like the hugest deal in the world, but we do have to make a choice, and you want to use the same choice in all your rectangles. So let's talk about it a little bit. We will see in the end that kind of the point is that no matter which way you do it, you're going to get the same total area eventually, right? The one on the right, like this looks like maybe a underestimate of the area under the curve because I have these gaps. Whereas this one's like an overestimate because some of the rectangle's parts are sticking out, right? But you might imagine that as the number of rectangles gets bigger, if they get skinnier and skinnier, these are going to be more close to each other, approximately equal, as n gets larger, as the total number of rectangles gets larger. So we will see it doesn't matter, but when we're doing a finite number of rectangles, we do have to care about which way we're going to do it. So we'll see it in practice, an example in just a minute. So all this data, how to set up Riemann sum. Once we have it all, the plan is just to add up the areas of all the rectangles. It's actually not too bad, right? All the rectangles will have the same base. Oh, I might not have said this before. I want to use the same width for all the rectangles, and I'm going to name that width this symbol. That's a delta x. So delta commonly is used to refer to change. The change of something is the delta. So the delta x is the change in the x. So that's just the traditional notation for it. It's just the name of the width of the interval. It's like one, you should think of it as like one variable. Like I could have called it like a w for the width of the interval, but it's traditional to use delta x. Okay, so all our rectangles have the same height, or the same base, delta x, and their height will depend on your function f and then your choice of left, middle, or right. So we're just going to do some multiplications. The width, delta x, times the height, which is f of 1, f of 2, depending on the function. So let's look at this example. So an object is moving a straight line. It has a velocity, v, given by this table. So remember, I said the function could be given by the table. Let's just think about this for a second, like with a graph. So at time 0, the velocity is here, and I'm going to call that 3.5. So that's sort of like one data point. At time, let's see, this goes 0.5, and then it goes 1, and then it goes 1.5, and then it goes 2, 2.5, 3. So we have all these data points, and I have different heights at each one. At time 0.5, we're at 2.125. So I'm not going to write all of these, but just to give you an idea. And at time 1, we're at height 1. Time 1.5, we're even lower, right? 1.25. So that's not a super detailed drawing. That's okay. I just want to give you an idea of what the rectangles are going to be, right? So I have to choose left or right, right? Let's see what they are asking. They say compute this number. So let's just read this, right? This is a little bit confusing, but when they say v parentheses 2.5, they mean v of 2.5. So we're plugging in the input 2.5 to v. So that's here. When t is 2.5, the output is this number, negative 0.875. That's the number that I'm going to be multiplying by 0.05. Or sorry, 0.5, 0.5. So that's the number that we can do. You know, it'll be like negative 0.4 or something, right? You can do the math. The question is, what does this have to do with Riemann sums? What does it represent? Well, v of 2.5, that's if I come over here. Apparently it's down here, negative 0.875. That's like this height. And if I multiply by 0.5, that's like the width of one of my rectangles. So let's say I was doing a left sum. Then I'd have a rectangle right here, which has a width of 0.5, which it does, because 2 to 2.5. Sorry, I said left sum, but I meant to say right sum. This would be, if I do it this way, it's a right sum, because I'm tying the height of the rectangle to this number, which is on the right side of this interval between 2 and 2.5. So this negative 0.4 number, that's like the area of this. 0.4 is the area, but this negative number, negative sign, is keeping track that it's below the axis. Okay, so this is sort of representing, so this is my velocity, right? The height, the v values is the velocity. So at every moment, I know my velocity. At this moment, sort of on this little time stretch between 2 and 2.5, you know, my velocity was about negative 0.8. In particular, at the end here, it was exactly negative 0.8. So I can say approximately, you know, on this 0.5 seconds, I was about negative 0.8. And so the total change of my velocity, the total distance that I covered was about this number. So I moved about 0.4 backwards over that interval. Okay, so if we were to compute the complete Riemann sum, we would want to add up a bunch of rectangles like this. I want to show you just a way you can kind of draw this on the graph. So, on the table. So let's say I was doing a right Riemann sum. So, right, this rectangle that I drew on the right, you can kind of visualize it as living between 2 and 2.5, which is like sort of here. So if you want, you can even draw rectangles sort of like on this table, if that's helpful to you. Right? What's the height of this rectangle? It's this number, negative 0.875. So I'm just remembering that this rectangle has a width of 0.5 and a height of whatever this number is. I kind of like drawing a dot on the right side to remember that I'm doing a right sum. If I'm drawing an actual graph, I kind of want this to be to scale. Like I would want this rectangle to be below the axis maybe, because it's negative. But here I'm just kind of schematically doing it to help me remember what multiplications to do. What other rectangles am I going to have? I'm going to have one that's like here, and the width is still 0.5, and the height is this number, negative 1. Really, so remember, this is really not to scale. Like I should draw a negative 0.8, the negative 1 is deeper than that. But this is just schematically like helping me remember. And I'm just drawing different heights, just so I don't get confused about which rectangle is which. So I have more rectangles. There's going to be one here with a height based on the value, the time 2. I'll have another rectangle here, height based on that. I'll have another rectangle here, height based on time 1, and maybe another rectangle here, height based on time 0.5. And I want to think about adding up the areas of all those rectangles. So we can just do it. The first rectangle is 0.5 wide times the height. Well, the height is this number, right? I'm using the right-hand number because I told you we were doing a right Riemann sum. So the height of the rectangle is 2.125, so that's my area. So whatever number that is, that's the total area of the first rectangle, and now I just have to add up all the rectangles. So the next one's going to be 0.5 width as well, times a height of 1, and then also again 0.5 times a height of 0.125, and it plus the next one's width is also 0.5, and its height is negative 0.5. I like to draw parentheses when I'm about to write a negative number. Right, so this is negative 5, or sorry, 0.5 times negative 0.5. Careful, if I wrote like this, it looks like I'm doing 0.5 minus 0.5. Even if I put like a times there, it's kind of confusing. So it's better just put a parentheses to make it clear. Okay, so I need 2 more rectangles, so I'm going to have plus width of 0.5 times the height of negative 0.875. That's one we did already. The last one will be 0.5 width times negative 1. So you can use like a calculator to actually get a number, but this is the process, right? I'm getting the area of each of these rectangles, and whatever number I get at the end, that's the total change of the total distance covered when I know my velocity function. Okay, so this is kind of tedious and a little annoying, right? We will be seeing very soon summation notation. That's going to be the point of that. A better way to do it, but it's good to be able to visualize at least doing this by hand and doing a couple examples by hand. I'll let you think about what would change if I told you to do a left sum instead. Basically, for the left sum, we're still going to have our rectangles. There's still going to be width of 0.5, right? But how tall are they going to be? Well, now the first rectangle, its height is going to be pegged to this value instead. The second rectangle, its height is going to be this value. So we're going to end up using just those ones when we're doing a left sum. So this is a little interesting thing. When we do a left sum, we sort of end up using all the values except for we don't actually use this rightmost value. That's okay. It just means that, right, because there's more lines there's more edges of lines than there are spaces, right? More dots than spaces. So one's always going to be left out. Like I said, the plan is to do, infinite number of rectangles, larger and larger number of rectangles, so that difference is not going to matter as much. But when we do a right sum, we sort of end up using just these numbers, right? So again, this left one is sort of left out. So that's another way to think about a right sum versus left sum, if that makes sense to you. Okay, so let's keep going and thinking about a better or another way to write down all this addition that we just did. Okay, so yeah, when we do Riemann sums, just like on the last example, we end up writing down stuff that looks like this. It's exactly what we had before, which is annoying. So this will be a little weird. Bear with me for just a second. Remember that, like, where do these numbers come from? These 3.5, 2.125? They came from the table, right? They were the y values, or, the v of t values in this table. So, like 3.5, right? or let's say 2.125, this number, that number is v of 0.5, right? At time 0.5, my output was 2.125, so v of 0.5 is this number. And all of these are v of something. 1 is v of 1. 0.125 is v of 1.5. Right, so we're really writing down like all these v of different things. So, right, if we were kind of working towards abstracting this a little bit, we could write down something like this, right? We have v of time 0, v of time 0.5, v of time 1, v of time 1.5, etc. And it's just thinking of this way is just a little bit more uniform, right? It's every single term is v of something, and then times the same thing, right? In fact, yeah, it's always 0.5 times something. So each term is sort of the same format. Now, we can actually do even better than that, right? So this is going to look a little weird for a second, but like it's not just v of something. These v's, their inputs are changing in a regular pattern, right? Because I had these evenly spaced rectangles, the first one's at 0, the second one's at 0.5, the next one's at 1, right? I'm adding up a half every single time to this like list of numbers. And I'm also starting from 0, right? So we could think of this as, my starting point 0, and then I'm going to take 0 steps of size 0.5, right? It's a funny way of saying 0, but like, right, we have this list of numbers. I'm starting at 0, the next one's 0.5, the next one's 1.0, or 1, and then 1.5. I want to think of these as starting from 0, starting from my left point, how many steps to the right did I take? At the beginning, I take 0 steps to the right. So that's just 0. But then the next term, where's this 0.5 coming from? It's starting at 0 and then taking 1 step to the right of 0.5. The next one, I'm starting at 0 and then taking 2 steps to the right. Starting at 0, taking 3 steps. Starting at 0, taking 4 steps. Starting at 0, taking 5 steps. So let's use a little bit of notation here. So I'm going to use the letter I, to represent the number that's changing here, right? Like what's changing every time, right? The 0 is staying the same. These 0.5s are sorry, when I say every time, in each term, what's the same and what's changing? This starting point thing, the 0, is the same every time. So I'm going to just start writing something down. That v of 0 is the same every single time. The plus is the same. This number 0, 1, 2, that's like a blank. That's changing every time, right? First it's 0, then it's 1, then it's 2, then it's 3, then it's 4, then it's 5. This 0.5, that's like my step size. That's staying the same every single time. And then this outside number, 0.5, that's also staying the same every single time. So every single term looks like this, is the point. And in math, we don't like to have blanks because it's a little bit hard to read. So people usually use letters for the blanks. So we're going to use the letter I to represent this blank spot. So what I'm going to write is 0 plus I times 0.5. And whenever you write that, you should kind of like think like what's your range of i's. You know that I is going from 0, I could be 1, I could be 2, and you know you're going all the way up to what's the biggest one? I could be 5. That's the largest number that we could have. So I wrote these dot dot dots because it's common to write that if you're not sure how many numbers you're going to do. But you could also just like list all the possible numbers. So this is a common notation. You'll see someone write You might see me write I is equal to 0, comma 1, 2, 3, 4, 5, sort of meaning it could be any of those. I might write something like 0, comma 1, comma dot 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 0.5, indicating that it's the same pattern, right? Increasing by 1 and then ending at 5. You could also write this if you wanted. I is greater than or equal to 0 and less than or equal to 5. So it's between 0 and 5. And we will see in a second that another way to write this is I equals 0, sort of 2, 2, 5. We're going to say 2 out loud, but we're not really going to write it. So we'll see that in just a second. So the point is we have the same sort of template. Every single rectangle can be expressed like this. The only thing I need to change to refer to a different rectangle is change this I. If I say I is 0, that's the first rectangle. And if I've like pre-programmed in like what V does, and if I know that it's always 0 and 0.5 here, then that's like going to be like a formula for the area of a given rectangle. If I want rectangle 0, I is 0. If I is 1, that's rectangle number 1. Let's actually see that really quick, just like with a different function example. So this V is maybe a little confusing because it's coming from a table. But if we had a specific function, like with a formula, say we were doing like x squared plus 1, right? That's a perfectly normal function. I could graph it. It would look something like this. I could think about doing Riemann sum, right? Drawing a bunch of, let's say, a left sum. Let's say we're going from -1 up to 2. So I could think about getting the area of each one of these rectangles. Well, in this like notation, I'm going to be adding up a bunch of rectangles. And there's, in here, I've drawn 4 rectangles. So there's going to be I equals 0, 1, 2, and 3, because I want to do 4 rectangles. So it's common to start at 0. So rectangle number 0 will be this one. Rectangle number 1, rectangle number 2, rectangle number 3. I'd like to write down like a formula for the area of one of these rectangles. I can do it using this idea. Right, we know we're starting at -1. I know every time I'm adding I copies of the width. What's the width of my rectangles? Well, here, because there's 4 of them and they're evenly spaced between -1 and 2, like this, I think the width is going to be 1, right? It's like 1, 2, 3, 4. Yeah, so I've set them up to be width 1 rectangles. So times the width of 1. Right, so when I is, right, sometimes people write like xi for this, meaning what are my different x values. This is just a way of indexing what my different x values are. I runs from 0 up to 3. When I is 0, my x value is -1. When I is 1, my x value is 0. When I is 2, my x value is -1 plus 2, so I get 1. And then when I is 3, I have -1 plus 3, which is 2. So, like, I could call this x0, x1, x2, and x3, and they're just naming what are my different x values. So I'm having like this list of x values. I know from this example we did before that what am I doing with these x values? Right, I'm doing a left Riemann sum, so I'm plugging them in to my function in order to get the heights of these rectangles. So this is so far the same as what we've done before. I'm going to do f of these xi's. So you might write f of xi, but typically the plan is to actually plug this expression in. So f of -1 plus I times 1. I could simplify that to just I, but I'm leaving it there right now just so we can remember that this 1 means something. It's like it's the width of one of my rectangles. And then what else do I need? right? This was the height of my rectangle, and this was the width. So I need to times by the width. So just like we said a second ago, the width of the rectangles is 1. So maybe I should have picked a little bit less, a better example, but it's fine. So far this is the same as we had before, but now because we have a function that has a formula, I can imagine like f of this formula. That means plug that formula into f and see what happens, right? I can plug this expression into f, multiply everything out. We'll do that in a second. We'll get a formula popping out, and that formula will actually tell us like the area of rectangle number I as a function of I. So let's see what that looks like. If I plug this input into f, that means I take the function f, and wherever there's an x, right, that's my input. Wherever there's an x, I write down the input that I'm plugging in. So this is like x in place of x right here. But x is squared, so I got to square this. And then I'm going to add 1. All right, this is like my formula for, so this is equal to that. F of x is x squared plus 1, so f of this is this squared plus 1. And I can I can simplify this, right? So let's just multiply this out. Remember we got a FOIL, right? So I could write this as -1 plus I. Let me scroll down. This is -1 plus I times -1 plus I. That's what the squared means. Then there's a plus 1 over here. We FOIL, right? Multiply the first thing. So -1 times -1 is 1. Multiply it onto the second thing. So minus I. Then I multiply the middle one. So I times -1 is -I. And then I multiply the last one. So it's I times I. So that's I squared. And then I still have this this plus 1 right here. Just simplify that. That's 2 minus 2I plus I squared. So we have this like formula in terms of I. And what this formula is telling you is the area of rectangle number I. Right? I have these 4 rectangles here. And if I wanted to know what the area of the first one is, I just plug 0 into this, right? When I is 0, we get 2 plus 0. So the area of that first rectangle is 2. But if I is 1, we get 2 minus 2 plus 1. So we get 1. So the area of that rectangle I, number 1, is 1. So we have a formula that's telling me the area of all these rectangles as a function of I. I just want to add all those up, right? Right. The plan would be to do I is 0, I is 1, I is 2, and I is 3, and just add them up. Let's just do it while we're here. So it's 2 minus 4 plus 4, so that's 2. And then when we plug in 3, 2 minus 6 plus 9. So that's 5, I think. So my total area, I just have to add all these up, right? 5, 6, 7, 8, 9, 10. Apparently, the area under that random function I wrote down, when I have specifically 4 rectangles, and I'm starting from -1 to going up to 2, all like this, all this setup that we did, I get area of 10. But what's neat about what we did is that, like, once we have like, you know, this part written down, with the idea that we're gonna like expand it in a second, maybe. Like the plan is just to add up for all the different I values this like same expression every single time. So we have a notation for that. So there's this sigma, capital sigma, and it's used to refer to adding up a bunch of things in a way that maybe depends on some index. So this I is called an index. It tells me like which term we're currently on when we're adding, right? Same I is down here. So when we have this, what this means is I goes from so I equals 0 on the bottom tells you that you're starting at I equals 0, and the 5 on the top means you're going up to 5. So you could maybe imagine writing I equals 5 on the top, but people don't. It's just shorter to write this. And it's understood that you're adding 1 every time. So if I see a 0 and then a 5, that means it's 0, 1, 2, 3, 4, 5 specifically. It's always adding 1. So we know we're adding up 6 things. Right? 6 things, right? 0, 1, 2, 3, 4, 5. There's 6 objects here. That's easy to mess up. When it goes from 0 to 5, that's actually 6 things. Okay, so we're adding up 6 things. What things are we adding up? Well, we're adding up the stuff that's like to the right of the symbol. And it's this formula that we saw before, right? It's the height of one of my rectangles, the ith rectangle, and then times the width of that rectangle, common width. So when I have this expression for something which changes depending on an index, I can use this notation to mean I'm going to add up all those things across all the different, all 6 indices. So this is just short for like something like this, adding everything up. This notation actually comes up all the time in math, and this might be the first time you've seen it, so it's good just to look at a couple examples. So let's look at, these are not going to be about Riemann sums, just about the notation, but we can still think about what the notation means. So this says, so you should always read this as a sum. I would say the sum from I equals 1 to infinity, sorry, not infinity, the sum from I equals 1 to 100 of I. So whatever this expression is. So this is the sum as k goes from 1 to 12 of 2k. This is the sum as j goes from 0 to 3 of 2j minus 2. You'll see we can use different variable names, and that's fine. I is the most common one. So I goes from 1 to 100. So I'm adding up 100 different things. Right? So that's why this is powerful. This is a really compact way of writing. I'm going to add up 100 different things. What 100 things am I going to add up? Well, I look at my formula, which might depend on the index. So here the formula is just I itself. Here the formula is 2k. Here the formula is 2j minus 2. I look at what the value of that formula would be depending on I as I is growing. So we can like write out the first couple terms, right? Let's actually maybe, yeah. So I can write out the first couple terms. The first term, right, what's this going to be? The first term is what happens when I is 1, because I know that's the starting value. When I is 1, I look at this formula I, and it's just 1, right? So it's a little confusing. It's kind of so simple it's confusing. But like on this one down here, the first term is going to be k equals 1. And I look at my formula which says 2k. Okay, well, when k is 1, that means that's 2. And I go to my next term, k is 2. And I look at the formula, k is 2. Okay, so 2 times k is 4. And I'm going to be adding these up. For the example 6 on the top here, first I is 1, and the formula is just I, so it's just 1. And then I is 2, so I look at the formula, I is 2, so I add 2, and then I keep going. I is 3, I get a 3, and I could write plus, dot, 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 one last plus to indicate the last number I'm going to add up. The very last one is when I is 100. And my formula says 100. So I put a 100 here. So this little expression is just short for add up every number from 1 to 100. So it's kind of cool to have like a short way of expressing that. If you do any programming or anything, you should just totally think of these as like a for loop where you're adding maybe every time. And you have this index I, which is tracking which part of the loop you're on. Let's keep looking at number 7 for a sec. So we did the first couple terms. It's usually good enough to write the first couple terms. You'll see what the pattern is. The next one, k is 3, so I get 6. K is 4, so I get 8. Okay, it looks like we're sort of adding 2 every time. What's the last term going to be? Well, when k is 12, 2k, that's 24. So I'm adding up the numbers from 2 up to 24. So I'll just go through this one quickly. So j is 0 to 3. So I do 2 times 0 minus 2. That's sort of the first term when j is 0. Then I do 2 times 1 minus 2, because j can be 1. And then 2 times 2 minus 2, because j could be 2. And then the last that j could be is 3. So 2 times 3 minus 2. And then I could work out what number that is, but it's some number, right? Okay, so if you want to practice this notation, I would say try writing out the sums and finding the totals for these two right here. It's also a good exercise to try to go backwards, right? If I start with a list of numbers like this, try to find a way to a sum notation like this that would generate that same list. So I think I will skip those, but let you try them if you'd like. So what we did up here is a little bit tedious, but good to get a feel for what the sum is actually doing. There's some nice shortcuts and sort of rules that we can use with this notation, which are super useful. So let's just look at a couple examples. So this first one, constant multiple rule. So let's look at this one. I have the sum of, from k goes from 1 to 4, of 2 times I. So let's just write out the first few terms. K is 1, first of all, so 2 times 1. Then k is 2, so 2 times 2. And then k is 3, so 2 times 3. Add that times 1 back in. And then k is 4, so 2 times 4. So, like, right, the name here is a hint. I have these 2's. Every single term has a 2 in it, right? So I could do 2 and then plus 4 and then plus 6 and then plus 8. But we can also do factoring, right? If every single term has a times 2 in it, that's the same as pulling the 2 out of everything and writing what's left over, right? So it's 2 times the total quantity of 1 plus 2 plus 3 plus 4. Right? If you imagine distributing the 2 back out, you'd get the expression on the left. So we can like pull this 2 out of each term. So, you know, in this example, it's not maybe the most useful because we can, these are numbers, you can just do them. But that suggests a general rule, right? If I leave this 2 out front for a second, remember how could I express this sum? It's a repeated sum, 1 plus 2 plus 3 plus 4. Well, we know how to do that. I can do I, where I starts at 1 and goes up to 4. So that looks an awful lot like what we started with, except it looks like I took this 2 and just like pulled it out in front of the sum. So you can always do that. As long as if you have a constant, then you can always do that, and that's like a nice shortcut. So for example, if I had a sum that was like 3 times k squared, it's the same as the sum 3 times the sum k squared. And maybe that's a little bit easier. So that's supposed to be a squared. So as a general rule, you can write this. So the idea is hopefully clear from maybe this example, but this is written just a little bit generically. C means it could be any constant. So not k, not n, right? It's not a variable. It's not something that's changing in every part of the sum. It's a constant. I'm just not committing to what number it actually is because it's supposed to be a general rule. And this AK just means the kth term. Whatever your formula is, which might depend on k. So you can always pull a constant out of the front. That's actually relevant to this Riemann sum stuff that we're doing, right? Do we have constant multiples up here? Yeah, because every single term has this same width of the rectangle, delta x thing, every single time. So if I wanted to, I could totally pull that out of the front, leaving everything else the same. And that would be like a legal algebra move. It turns out people actually usually keep it inside when you're doing Riemann sums, but that would be a legal move. And that would be kind of like if noticing back at the beginning that there's 0.5s everywhere, right? So like maybe we might as well pull the 0.5 out in front first before writing down our v's, right? Which you could totally do. And in fact is a good way to save time if you're doing it by hand. Like if we do up here, right, I don't need to multiply every single term by this 0.5. I could add them all up and then multiply everything by 0.5 at the end. That's a good time saver. Okay. Another use for rule is the addition rule. So this just means like noticing if I'm adding up a bunch of terms and each term itself is the sum of a couple of things, then I can, in fact, sort of add them up separately, right? So let's write out the first few terms of this. First, there should be an I. First I is 1, so we get 1 plus 1 squared, and then 2 plus 2 squared, and then 3 plus 3 squared, and we go all the way up to 4. 4 plus 4 squared. Okay. Just notice I could regroup this, right? Because when I add stuff, the order doesn't matter. I could like pull out this stuff if I wanted to. Right, 1 plus 2 plus 3 plus 4. And then what's left over is the other stuff, right? 1 squared, say, plus 2 squared plus 3 squared plus 4 squared. And I could just notice that these are their own sums, right? This first one is adding up i's as I goes from 1 to 4. And then the second one is adding up, well, I squareds as I goes from 1 to 4 as well. And so what it looks like happened as we go from here to here is I sort of broke up like the inside by putting the sum on both parts. Like it looks like it just sort of distributed the sum symbol onto both parts. And that's something you can do. That's a rule that you get to use. As like a general rule, we can write this as here. If I have the sum of some stuff where the terms themselves are something plus something else, that's the same as the sum of the first thing plus the sum of the second thing. So just for example, if we had like, k squared plus 7k plus 1, I could rewrite that as sum of k squared plus sum of 7k plus sum of 1. Right, I didn't say what the index was. Let's say k is 0 to 10. The same indices would be here, right? 0 to 10, 0 to 10, 0 to 10. So that's, you're allowed to sort of break it up across the sum like that. We can start combining some of these rules together, right? Like we have this constant multiple rule from before. So I could pull this 7 out, right? So I have this sum of k squareds plus 7 times the sum of the k's. Plus this is still here. So you can start kind of combining these rules. And what's kind of nice is we will see in just a second, there are actually sort of shortcut formulas for some specific common terms. And we won't do a ton of this in this class, but sometimes you're asked to like evaluate like a big sum like this, and the kind of the idea is to break it up like this and evaluate the individual pieces. One of them is pretty straightforward. If we look at this last term here, it's k goes from 0 to 10 of 1. Right? So there's no k in here. That's okay. It just means that my formula, when k is 0, I'm adding the number 1. When k is 1, I'm adding the number 1. When k is 2, I'm adding the number 1. So my thing I'm adding doesn't happen to depend on k, but that's okay. So it's really short for 1 plus 1 plus 1 plus, 10 or 11 times, actually, right? Because I'm going from 0 up to 10. So I'm adding up 1 11 times. That's 11, right? But if I had like a 2 in here, I could be getting twice that much. So that's like the first useful shortcut. If I'm adding up a constant, n copies, right? The first one, the second one, the third one, all the way up to the nth one. That's the same thing as my constant times n. Right? So like, for example, if I'm doing k equals 1 to like 10 of like 2k, then, or sorry, of 2, k equals, adding the constant 2 every single time, but I'm doing it 10 times, I'll get 20, which is 2 times 10. So this n number is the same number that's in the top. There's a couple other nice shortcuts here. I'm not going to get too much into these. Basically, like, for example, if we look at this one, it says the sum from k equals 1 to n of k. So first k is 1, and then it's 2, and then it's 3, plus dot dot dot. And so I'm adding up the numbers from 1 to n. So 1 plus 2 plus 3, or 1 plus 2 plus 2 plus 4 plus 5, or something else depending on my top number, n. It turns out, if you think about it for a little bit, you can prove that there's always like a consistent formula for getting what that total is. And that formula depends on that top number, the number you're stopping at, n. And it turns out that that's this number. So for example, if I'm adding up the numbers from 1 to 100, which is what we were doing earlier, it turns out I use 100 as my n. So 100 times 101 divided by 2, which is this 2 and this 100 can cancel to make 50 times 101. And that's 5,050. So yeah, it turns out if you add up the numbers 1 to 100, you get this. And you could do some similar sums and get some numbers. So like if you were trying to total up something like this from earlier, you could use that like right here. So if you ever do like a discrete math class, these come up more. They'll come up a little bit for us. I won't dwell on these too much. You could do the same thing, but instead of adding up k squared. Right, it's like 1 plus 2 squared plus 3 squared, etc. And there's also a formula you can come up with. You could also add up cubes. 1 cubed plus 2 cubed plus 3 cubed. And the formula is that. So if you ever need to use those, there they are. Okay, so we've seen our Riemann sums. This picture, our rectangle heights. We talked about adding up all the rectangles and sort of writing this sum notation. I want to just kind of bring it all together and express our Riemann sums in the sum notation. So we basically did it already, but just kind of like all in one spot. Remember we had this example. I want to focus for a second on the 0.5s. Those were our widths of our rectangles, right, which we called them delta x. And notice that there's a delta x on the inside also, right? So it's 0 plus I times delta x. And it's actually super common to name this xi. That's like what we were doing. We did that a little bit earlier. If I call that xi, then I can write this whole thing as the sum of v of xi. So that's taking something like this and plugging it into your function v, and then multiply by this constant delta x. So what's nice about this is that it's just a pretty short formula. Like as long as you know what xi means and you know what delta x means, then it's a pretty short formula that really gets the whole area of all those rectangles. This is the first 6 rectangles all added up. Could be expressed compactly with this formula. And some problems will ask you to just like set up a Riemann sum, and the idea is to like write this down. And if we want to, we can actually use some of these shortcuts from before to compute a value for it. So let's see what that looks like here. In this example, let's compute a left Riemann sum for this function, f of x equals x squared, on the interval 1 to 2, using 4 rectangles. So right away, we just have to figure out that kind of list of information that we were going to start with. I think it's best to figure out the delta x first, the width. What's delta x going to be? Well, we know it's the interval 1 to 2. We know I'm going to do 4 rectangles. So already I know what this should be, right? Like this should be 1.5 if I want them to be evenly spaced. And then this better be 1.25. And this better be 1.75. So you can kind of work it out like that with small numbers. But there's a nice, just quick little formula which can do that, kind of do that math for you. Oh, right, our delta x here, like it should be 0.25, right? That's the difference, the width between each of the tick marks. This is just a quick little formula we can do, which will spit that out for us, so you don't have to like draw this picture and think about it every time. So that formula is going to be, I'm going to write it like b minus a divided by n. Okay, what are these letters? A and B are your endpoints. So this is A, and this is B. So right, I'm starting at A and I'm going to B. How far is that? Well, it's 1 here, right? It's 1 wide. One way to see that it's 1 wide is to say, well, it's going from 1 to 2. So like the distance from 1 to 2 is the number 2 minus 1, which happens to be 1. But like if I told you my interval was like 5 to 99 or something, how wide is that? Like, well, what's 99 minus 5? It's 94. Okay, so it's 94 wide. And you can kind of do that sort of mechanically without having to think too hard about it. So this top number, b minus a, is just telling you the width of your interval. And then dividing by n, well, n means how many rectangles am I going to do? So here n is 4. Right, I take this total width right here, it was 1, and I'm going to divide that 1 by 4, because that's how many rectangles I want. When I do that, I'm going to get my 0.25. So it's just the total width divided by how many rectangles there are, gives you the width of each rectangle. So it's just a good idea just to have this like in your brain, and just start your problem by writing that down. And then we can fill. So let's just fill in an RB minus a over n. So b is 2, a is 1, we're going to divide by 4. So we already know it's 0.25, but it's just good to see this. So that's 1 divided by 4, that's 0.25. Okay, great. So we have delta x, so we're already halfway there. We need to write down what my x values are, right? I have the first, sort of the 0th x value, that's going to be 1. It's going to be x1, x2, x3, and x4. And actually, because it's a left Riemann sum, I'm only going to end up using these 4. But that's okay. Now remember, we're trying to use the sum notation. So I don't want to, like I could just write the numbers down, 1.25, 1.5. But I don't want to like have to add all that stuff up by hand. I just want to write the sum notation, which means I need like a xi formula. And this is the same thing that we did before. it's this idea, right? Again, just like the b minus a over n, you can just have a formula in mind for this. It's always going to be a plus I times delta x. Right, a is your starting number, so like 1 in this case. Delta x is your width, and I is just which term you're on. Right, this is like a formula. If you plug in different i's, you get different x values. I want the 0th one to be a, my starting number. And then when I is 1, that's a plus 1 delta x. When I is 2, it's a plus 2 delta x's. So having 2 steps to the right. That gets me your x2, and etc. So there's like a formula for which x value you're at. The point of this, writing it this way, is we're going to like plug it into our function, and it will be nice. So let's fill in our numbers. So a is our left number. This is, I guess I should write this is a and this is b. 1, I is like the variable, it stays. Delta x is 0.25, so times. So you always want to write both these things down. What's your delta x first, and then what's your xi? And you can use these same formulas every single time. Just fill in your data. And then we're basically done. We just got to write our Riemann sum now. So we write the sigma. We got to figure out our range of I values. I told you before that we're only going to use these guys because we're doing a left sum. So this just be a little tricky. If we were doing a right sum, we'd want to use these 4 guys. So our first I that we want is 0, and the last I that we want is 3, because I wanted to use x0, x1, x2, and x3. So I'm going to write I equals 0 up to 3. It is a general rule that like if you're doing a left sum, this number is always like n minus 1. Right? N was 4 here. But it's good just to kind of think through it. And then the inside, I'm going to be plugging in my xi's into my function f, and then multiplying by delta x. So let's just write f of xi and then delta x. So this is like abstract. You're not done, but it's a good starting point to remember what to write next. Like you can always do this, and then we're just going to kind of expand it out. So the sum is the same. F of xi, I just need to expand this. That's f of whatever my xi is. Well, we figured out that was the xi. 1 plus I times 0.25. And then we figured out delta x also. It's 0.25. Now we're still not done. Just like before, I want to like actually plug this in to my function f and see what happens. So it's going to be sum, and I'll plug this into f. So it's f says square my input. This is taking the role of x, like this whole thing is taking the role of x. I'm going to square that. So 1 plus I times 0.25 squared. And then we still have times 0.25 out there. Let's just actually finish multiplying this out. So remember, we got to FOIL this. So first, 1 times 1 is 1. 1 times 0.25i. 1 times 0.25i. And the last term is I times 0.25 times I times 0.25. So I squared times 0.25 times 0.25. So I'm just going to write I squared times, so 0.25 squared, just if you want to do this in your head, it's a quarter, right? When you square a fraction, it's the same as squaring the top and squaring the bottom. And so it's okay it's totally fine to write fractions. So I'm going to have 1/16 right here. Okay, so that was kind of multiplying out that part, and then times 0.25. So if we want to be like super complete, we just finish here by including everything. Let's get our i's back in so we don't forget. I is 0 to 3. And let's just write all this stuff with quarters and stuff. So I'm going to have I squared over 16. So that's this part. Remember, times by fractions, the same as divided by the number. I have 2 of these, so that's 0.5, right? Because I can add them up. I'm going to write that as I over 2. And then I have plus 1. And that's all times 0.25. So I turned it into fractions because, or if we're doing fractions, that's 1/4, right? I turn it into fractions because I kind of like fractions better. But you can use decimals if you like, that's fine. Okay, cool. So if a problem asks you to like write down the Riemann sum, right? You're kind of like where should I stop, right? You definitely have to go further than here because this is just like the definition, but we haven't plugged anything in yet. This is good. You're seeing that you figured out what delta x is, you figured out what xi is, but you really want to actually be expanding this f, like plugging it into f. So I would want you to go to like here on an exam. Definitely like to show me you know what it means. You're plugging the xi into f. That's good enough for me. If you're actually doing this by hand and actually wanting to get a final result, you'd have to like go all the way to here and then go a little bit further using some of those sum rules from before. Might not look like it, but we can actually use those sum rules on this guy if we wanted to. So maybe just really quickly, first of all, notice that this 1/4 can get pulled out. Where we talked about having a constant multiple of everything means you can pull it out. This is I squared over 16. This is I over 2 plus 1. We also talked about how you can split the sum like across the different pieces, right? So you could have 1/4, and then let's get this out of the way. I have the sum of the I squared over 16 part plus the sum of the I over 2 part plus the sum of the 1 part. On each of these individual pieces, you could pull the fraction out. Well, like the first one is I squared over 16. That's the same as 1/16 times I squared. So I can pull that 1/16 out. So 1/16 times I squared. So I goes from 0 to 3 still. The next one, I over 2, same as 1/2 times I. So I can pull the 1/2 out. Same index. And then the last one I'll just leave as 1. And then each of these individually, we can use those formulas that we had earlier. This last one was the easiest one, right? There's 4 things. It's 1 plus 1 plus 1 plus 1. So that's 4. This one, so it's a little bit tricky because the formula we had up here expects your index to start at 1, but we have starting at 0. So that's okay. We should just think of this as the first term is I equals 0, and then plus the sum from I equals 1 to 3 of I. And we know that the second part is 3 times 4 over 2 based on that formula that I just scrolled away from. It's n times n plus 1 over 2. So that's 6. So yeah, because the I equals 0 and the formula is just I, it actually doesn't change anything if you, like it's still this, because the 0 doesn't add anything. Okay, so this ends up being 6. And then for this third one, we have to scroll over here because I don't remember the formula. So it's k squared. Our n was 3. So it's going to be 3 times 3 plus 1 times, so 6 plus 1 is 7. And then divided by 6. So yeah, that's some number. The 3 and the 6 can cancel. So you'll have 4 times 7 over 2. And then the 2 and the 4 can cancel. So you'll have 2 times 7. So you'll have 14 total for that. So almost done. So this ends up being 14 sixteenths. This ends up being 6 halves. Right, so this is 1/16 times 14 is 14 sixteenths. 1 half times 6 is 6 halves. And this is 4. And we could turn this into a number. Let's just go ahead just because we're here. So we want to combine the fractions, right? So I want them all to be 16 denominator. So this middle one I have to multiply by 8. So it's 48 over 16. This one I got to multiply by 16. So it's 64 over 16. And you can add all these up. So 64 plus 48 is 112, I think. Plus 14 is 1, 2, 6. So this is totally calculated land, but the point is I'm trying to show that it's fairly concrete. Like you can get a number if you just work on it for a minute. So I think this is 126 over 64. So that's some number. It's around 2. So the area under that function is around 2. So like I said, you're probably not going to have to go this far. I won't make you go this far like on an exam. I'm happy to have you end up like here. But just know that you could do it by hand. And it's a little tedious, but it's not crazy as long as you have these formulas. So if you see a problem asks you to do that, that's what they're thinking of. Okay, just a couple more comments before we wrap up. So there are we did left sums in this example, but you can also do right sums or middle sums. So we talked about right sums. I didn't really mention middle sums, but it just means you're picking a value in the middle of the interval instead of on the left or the right. There's a slightly different formula. I'm not really going to worry too much about it, but you could maybe try to figure out a formula for it. So let's just look at this example really quick. Say we have on the interval 2 to 10, and we have 4 subintervals. So here's 2. We're going up to 10. We can figure out our delta x right away. Right? It's the difference, 10 minus 2, divided by the number of rectangles. So it's 8 divided by 4, which is 2. So that means my delta x is 2. And we saw before when we were doing a left sum, we want to start it at A, the left point, and I want to add up I times my delta x, which is 2. So that's hitting all these numbers. I'm hitting 2, I'm hitting 4, all the way up to 8. I'm maybe not getting the last number. If we're doing a right Riemann sum, right, we would want to start with my 4 and end up all the way at the 10. Right, I would want to go from 4, 8, 10. So this is kind of a minor point, but you could write the formula like this if you wanted to. Right, when I is 0, I want x0 to be 4. Right, I want it to be the first one to be that 4 right there. So I just need to make sure that my formula in terms of I spits out 4 when I is 0. So you still kind of want to start at 2, and you still want to like add 2 every time, but I'm going to be starting at something slightly different. So it's going to be like I plus 1 or I minus 1 kind of thing, but it's good to think through what you want it to be, right? If I is 0, I want it to be 4. So if I is 0, I want this to be 1. So it's probably going to be I plus 1. Now we can check. When I is 0, 2 plus 1 times 2, 4. Nice. But when I is 1, you get 2 plus 2 times 2. Yeah, which is 6. So that's starting off on 4 and then going to 6. So if you are using this sum, I goes from 0 to the end, and you want to do left sums, then you have to use this one. And if you're doing right sums, you have to use the one on the bottom. Alternatively, you don't have to use this indexing. You could start with I as 1 to n, and then use the same xi as before for doing a right sum. So it's just a matter of where you're starting and keeping track of what your xi stands for. So let me know if you have a question about that. It's not that big of a deal. I would say if you're doing a left sum, just use this formula. And if you're using a right sum, use this formula. Or if you prefer, you can use the original formula for a right sum, but you have to change the index. Okay, you can also write down a similar formula for a middle sum. I'm going to leave that as like a bonus if you want to try that on your own. Okay, so I think that's mostly what I wanted to say about Riemann sums. Let's just do this last example about a bacteria population. So a bacteria population increases at this rate given by this function. F of x is 3 plus 0.2 times x squared, millions of bacteria per hour. Estimate the growth in bacteria at an initial 10-hour period. Set up left and right Riemann sums. So just want to think, this is a story problem, right? They're telling us the rate, right? Coming back to what we started at the beginning, we're connecting rates to like total growth, right? This is like velocity. We have this total rate. We're going to get the total growth. We're going to do it by doing the area under the function, right? This function, it's going to look something like this if you graph it. And we're going from the initial 10-hour period, so from time 0 up to time 10. We're imagining the area under this curve. That area is our total new number of bacteria. We are imagining that we're going to be drawing lots and lots of rectangles. We're actually going to do 100 rectangles. And instead of writing down 100 things, we can just write down a sum notation, which will compute that for us. So as before, let's collect our information. We need delta x. We need xi. Delta x is b minus a over n. Xi is a plus I times delta x. So we got to figure out delta x first. What are our a and b? Well, a and b are our starting and ending time points. So we're starting at time 0, and we're going to time 10 because they said it was a 10-hour period. What's my n? It's my number of intervals. They said n is 100. So we can just plug all this in. B minus a is 10 minus 0. N is 100. So we're getting 10 over 100, which is 1/10. That's my delta x. And then for xi, what's a? It's 0. I is a variable. Delta x is 1/10. By the way, it's totally fine to write this as like I over 10. Starting at 0, right? Okay, so now we just start writing our sum down. So what's my range of i's? So we're doing a left sum, I think. Yeah, left sum first. So I think the easiest way is just to always do, for left sum, I equals 0 to n minus 1. Right, it's the 0th one, the first one, the second one, all the way up to the second to last one, because we're using the left endpoints. And then it's always going to be f of xi times delta x. This is sort of our template. Now we're going to plug in our information. N is 100, so we're going up to 99. F of xi, let's just write f of our xi's first. So our xi's is that. And then we figured out our delta x was 1/10. Now we're not done. We still have to plug this into f. Let me write this as the left sum. So keep this, and then let's plug it into f. So we just got to start copying down our function for f. But every time we see an x, plug in our input I/10. Now right here, we're going to write times by 1/10. Very tempting to just write that, but that would be wrong because of this plus, right? If you write this, it looks like you're saying 3 plus this product. But I really want this product times 10, right? So parentheses here. Okay, and that would be a totally acceptable final answer. You can go a little bit further by simplifying, right? This is 3 plus 0.2 times, when you square a fraction, you square the top. So you do I squared, and you square the bottom. You still have times 1/10. You could simplify even more if you wanted to. Like you could put this 1/10 in, 3/10 plus 0.2 I squared times this 10 goes on the bottom. So you get 1,000. You could combine these fractions if you want to. 300 plus 0.2 I squared. With that, you can go crazy simplifying if you want to. I'm fine with this. The stuff on the right is what you would have to do if you wanted to find the value by hand. It might not look like it, but this is already close, right? Or I could pull the 1,000 out using the constant multiple. Then I have 300, and I can separate the sums, right? I could pull the 0.2 out of the second sum. And we're actually pretty close to the version that we saw before. Sorry. With the I squareds and everything. So I'll let you think about that if you're interested. Okay. It also asked us to do a right Riemann sum. So I just want to show off that this is not a lot of extra work. We've already done all the work, basically. So for right sum, I would say just change the indexes. Go from 1 to n. So same thing. I goes from 1 to 100 this time. We can actually copy everything else down because it's the same xi's. So before I was talking about using a alternative xi. Another way to do this would be to keep the index 0 to 99, but have, instead of the xi that we had before, have this other xi, which was the same thing, right? Except that my xi's, sorry, I started writing 3 plus 0.2, that's from f. Right, I could use the different xi's, where instead of I over 10, it would be, right before, up here we changed the I from just being I to being I plus 1. So here it would be I plus 1 over 10 instead. And we still have the delta x. So the difference, right? These are both saying the same thing. If I start at 1 and use the old xi's, which was just I over 10, this would be f of I over 10, then that's computing the same numbers as if I start at 0 and do f of I plus 1 over 10. So whichever way makes more sense to you. So last thing I'll mention is that there are lots of calculators online that are like Riemann sum calculators, or sigma notation calculators. So if you just search sum notation calculator or something like that, you can plug in something like this and it'll spit out a number for you. So basically doing this last step here where you're doing like the sum formulas. That's why I'm happy getting to here, because there's plenty of calculators which can do that part for you. Okay, so that's all about Riemann sums. Thank you for listening. Good luck, and let me know if you have any questions. See you next time.